Welcome to lecture 4. In the last lecture we said that we are going to do a little bit of the thermodynamics of the interfaces. So, in this lecture thermodynamics of interfaces. Okay. So, let us consider a situation like this. This is bulk fluid 1, this is bulk fluid 2, this is basically the interface, and this is basically the dividing surface also between bulk fluid 1 and bulk fluid 2. So, the two bulk fluids are basically separated by an interfacial region. Okay. So, what can happen? There are several situations that can take place. One is that the two fluids may not actually mix with each other. So, immiscible liquids, it could be a situation like that. Okay. It is also can be taken that is a single substance and it is present in two phases. So, basically bulk fluid 1 and bulk fluid 2 are the same substance, but they exist in two different phases. So, it could be just water, liquid water and water vapor, for example. Okay. It could be also a mixture of gases, say for example mixture of gases in contact with a solid surface. It could be something like that also. It could be a chemical reacting interface. That means the two, this could be this bulk fluid 1 could be the oxidizer, bulk fluid 2 could be the products. So, it could be something like that. In that particular case, this interfacial region therefore becomes what we call the reaction zone. Okay. So, there are multiple such possibilities that can happen, right. Now, for single component system, what we have seen, let us just do a small recall from the last class or last classes. Basically, we saw that this happened. This we did in the last class, correct? Okay. This is valid for a single component system, right. Now, suppose the configuration of the volume and the surfaces 1, 2 and I, as it has been marked over here, are fixed. Okay. So, let us put that assumption in. Suppose configuration of volume and surfaces okay, 1, 2 and I are fixed. Okay, are fixed. So, in that particular case, if the volume is fixed, this term basically goes to 0. So, that means this dE will now become TdS plus mu dN. Okay. So, let us go to the next page. Okay. Now, so that is the configuration. Now, let us consider a scenario. Consider a scenario where some mass okay, and energy exchange, basically an exchange okay, occurs between bulk fluid 2 and the interface I. Got it. However, there is no exchange between bulk fluid 1 and interface. Okay. So, that is I think the typical scenario that we are considering over here. So, some mass and energy exchange occurs between the bulk fluid and the interface I, but there is no exchange that is occurring between the bulk fluid 1 and the interface I. Okay. Now, the total energy, now as we know that the total energy of the system should be constant, basically remain unchanged, right. Let's pick a different marker. So, that E total, the total energy is basically given by the interface energy plus E1 plus E2, right. Okay. Now, because of this exchange that has happened between the bulk fluid 2 and the interface I, the energy in the region between 2 and I with the energy at 1 is held constant. So, therefore, any change in the total energy, which is of course equal to 0, is basically brought about by a change in the energy of 2 plus the corresponding energy of EI, okay, and that is basically equal to 0, right. So, the concept here is nothing, it is very simple. The energy, there is an energy exchange that is occurring between this and this essentially, while this is basically kept constant. So, there is a reduction or increase, whatever it may be, of energy of E2. There is an equivalent increase or decrease of energy of course of the opposite sign of EI, but the total energy of the system is constant. So, therefore, the sum total of these two energies has to be equal to 0, right. Individually, of course, dE1 is of course equal to 0, because we are not having any exchange between the bulk fluid 1 and the interface I. So, hope this part is actually clear. Okay. Now, what this means is that if we substitute expressions for E for each of these E2 and EI, what it will give? dI plus mu I dNi plus T2 ds2 plus mu 2 dN2. This is equal to 0. This part should be quite clear, right. What we have done is that basically we have substituted the same relationship, right. So, that is the expression that we get out of this. Now, since mass and energy both are exchanged, so there will be a change in the number of moles also, though the total number of moles in the system remains constant, right. N total is basically a constant, is not that so? Okay. Because the total number of moles cannot change, right, it is like a mass conservation. So, here of course, if we do this dN total, okay, this is of course equal to 0, and this 0 is brought about by this dNi plus dN2. Once again, the number of moles of N1 has been kept constant, because there has not been any mass or energy exchange, right. So, that is a simplified kind of a process. So, dNi is equal to minus dN2. It is a very similar kind of a statement like this energy equation. Okay. So, up to this point should be clear. So, now we look at the corresponding entropy balance. Let us look at the entropy balance. Okay. Now, S total, okay, is basically given as Si plus S1 plus S2, this is equal to a constant, right. So, ds total is equal to 0, which is basically brought about once again by the change of entropy of the two interfaces, because ds1 was already equal to 0. So, from here we can infer dsi is equal to minus ds2. Okay. So, if we rewrite now the expression that we saw in the previous slide, let us just look at it. just in the previous slide, if you look at this expression now, what we can do is that we can cast them in terms of one variable only, right. We can, because we have ds2, we have dsi, we have dni and dn2, okay. So, we can try to cast them in one particular form. So, by using these relationships like this, okay. So, if we do that, then this becomes ds2 plus mu 2 minus mu I dn2 is equal to 0. Okay. This is valid for any ds2 and dn2. Got it? Okay. Since this is valid for any ds2 and dn2, individually these two terms must be equal to 0 individually, right. So, this leads to the statement that T2 must be equal to Ti, because this is valid for any ds2 and dn2, right, and similarly your mu 2 must be equal to mu I, right. Now, similarly here we have held bulk fluid 1 as constant. Let us do this, if we extrapolate and do this between bulk fluid 1 and the interface, you will get an equivalent relationship which will be like if you want to go for that, it will be T1 must be equal to Ti and mu 1 must be equal to mu I, right. If we just assume exchange occurs between 1 and I, right, and 2 is held constant, correct. So, explicitly what this gives you, T1 is equal to T2 equal to Ti, mu 1 is equal to mu 2 equal to mu I. Okay. So, this is the key expression for that interface. That means, the temperature of the interface should be the same as the temperature of the two phases, right, which are with which it is in contact. Similarly, the chemical potential of the interface is the same as the chemical potential of the other two phases that are present, right. So, this is an interesting observation, okay, or an interesting inference that we have drawn out of this particular work. Okay. Now, let us look at, while we are at interface, let us look at an important feature of an interface which is called surface tension. Okay. So, surface tension is a thing that you will encounter not just in it is a quantity or it is a parameter that comes in handy in any type of multiphase flows, like with droplet, bubbles, whatever it is, right. For example, we already saw a few features, like for example, if you have a droplet sitting on a solid surface, right, there is surface tension between this, that means that this is liquid and this is the vapor, say for example, right. So, there is surface tension between the liquid and the vapor. Okay. There is also surface tension between the liquid and the solid and the vapor and the solid, right, and this is what in common parlance people call the three phase contact line. So, surface tension is the one which allows this droplet to maintain its shape. Okay. So, it is not just the liquid vapor surface tension, it is the liquid solid surface tension or the vapor solid surface tension, okay, that allows it to form this kind of a shape. So, when you actually inject, for example, say you assume that this is like a tower in which there is a flow and you inject a droplet into this tower, right. So, if you look at the droplet and if this flow rate is small, this droplet will be nice and spherical, right. So, that spherical shape of the droplet comes precisely due to the surface tension. Okay. So, of course, I have assumed a low speed flow, so that there is no distortion of the shape. Okay. So, normally not if the droplet is not under under any external stimuli, like for example aerodynamic stress and other things, it will remain nice and spherical. So, this shape is due to surface tension, right. Okay. So, there are similar such things when you actually have pool boiling, that means the surface is heated, you supply heat to a surface, all these bubbles, you have seen bubbles, right, when you actually warm water in a pan, right, when you boil water in a pan you see all these bubbles coming up, right. So, these bubbles are also spherical in shape, okay, to the best of the. So, once again if these bubbles will be spherical in shape so long there are no external stimuli doing otherwise. So, these are also spherical and these are also due to surface tension, right. So, surface tension as we can see is one of the most important parameter. It works not just for free droplets and bubbles, it also works for droplets on substrates, okay. These are called sessile droplets. We will spend a few lectures on this kind of droplets as well. So, the sessile droplets are extremely important, okay. Now, for analyzing the surface tension we basically use the same form that we had earlier. That means this is 1, this is 2 and this is basically the interface. Okay. So, surface tension is not just for spherical droplets, it can happen for any types of structures also, okay, liquid structures also. Okay. So, here we have taken of course an arbitrary kind of an interface. Okay. So, it is a liquid vapor interface and it is often marked with a level of high discontinuity. That means across, for example, if we take this droplet into consideration, okay, this is liquid, this is vapor, the density, there is a density jump across this interface. So, there are many of the properties undergo a sharp jump. So, if you want to just plot the density, for example, if this is the bubble, if this is the droplet. So, if we have something like this, the density will be very high and this is rho and this is for example, this cut section, let us term it as a x. What will happen is that the density will be very high right up to the interface, okay, then it will attain a sharp drop, right, and it will come to a value over here, and this drop in the case of liquid and vapor is of the order of 1000, right. So, similarly many of the properties actually change because of this. Okay. So, it is a region of sharp discontinuity, the properties changes, okay, the properties between the different phases actually occurs over a thin, but it can be considered to be a finite region. So, thin finite region. Okay. So, the analysis that we are going to do over here is very similar to the analysis that we did just a moment ago. So, the number of moles, if you consider a situation like this, the number of moles of the interface basically is Ni, is basically N total minus N1 minus N2, right. This is the total number of moles that are present at the interface, right. Similarly, internal energy, we can take it as EI, that is the internal energy of the interface, that is E total minus E1 minus E2. Okay. Right. So, this should be quite apparent, this we just did a few moments ago. So, the interfacial energy and the number of moles that are present at the interface is readily visible. Okay. Now, let us go to the next slide, and EI therefore is a function of both SI, that is the entropy, and the number of moles of the interface, okay, which is valid when the shape and location of the interface is flat, valid for interfaces okay, of fixed shape and they are flat. There can be more complicated interfaces. If the interface is deformable, okay, if it is a deformable. So, you understand the interface is fixed. So, it is as if whatever exchange that is happening between the two phases, okay, the interface is remaining kind of a fixed in space. So, it is almost like a hard rigid kind of a wall kind of a thing, okay. But if the interface is deformable, which is in most cases the interface is deformable, right. The droplet surface can actually, if you take a droplet like this, if you apply some kind of a force on it, the droplet surface can actually corrugate or do something like that. So, this interface is becoming a deformable interface, right. Okay. On the other hand, if you just allow this droplet to sit nice and easy, okay, this interface is like a fixed interface. Okay. If the interface is deformable, both the shape and the area of the interface affect the internal energy. Both shape and area of the interface affects the internal energy. In that particular case, what happens is that we can say that EI is basically not just a function of two parameters, it is SI NI comma A and K also. What are A and K? A is the surface area and K is basically the curvature. So, and this is the surface area of the interface. Okay. So, what we can see over here is that if the interface is not deformable, there can be situations like that also. Okay. It is only given by a function of two parameters. However, when the interface is actually deformable, okay, then the surface area and the corresponding curvature comes into the picture. Of course, here in this case the interface has got a curvature. So, it does depend on the K, the curvature, but if it is like a flat interface like this, okay, this curvature part does not come into the picture. Flat can be, for example, when you are evaporating. So, you have a flask, okay, you have a pan and there is evaporation that is happening from the surface, correct, right. So, this interface is flat and it is not deforming per se, it might translate up and down. So, in that particular case, in this kind of an interface, it is given as EI SI comma NI, right. Whereas, in the case of a droplet which is not deforming, but still it has that curvature. So, here EI will be EI SI NI and probably K, okay. And of course, you have the surface area of the interface also coming into the picture in this case, but if it deforms, okay, this area change, it is of course a function of area also. When it deforms, then this area change becomes an important parameter, that is this area change then becomes an important parameter. Okay. So, the interface is like that. So, whether it is deformable or non-deformable determines a lot of things. Okay. So, let us go to the next one. So, the change in EI, that is what we are interested in, that is the change in the energy of the interface is basically given as dE. Once again we can write it like this, right, N A and K. K here is a curvature and this is of the interface only, recall. Okay, so, S A and K, then you have this with respect to A, S N K d A plus okay, fine, right. So, what does it tell you? The change in energy of the interface dI basically depends on which parameters? It depends on the change of the interfacial energy with respect to the entropy, and we will see what that term exactly means. change with respect to the number of moles at the interface, right. It also depends on what we call the change in surface area and the change in curvature, right. So, once you, coming back to that droplet example, once you deform the droplet to a pancake, say for example, right, by whatever means. So, what you change? You change two things basically, you change both the area, this is area A1, this is A2. So, A2 is obviously greater than A1, right. Also the curvature changes, here it has got one curvature, here it has got two curvatures essentially, right. So, the curvature also changes. So, both A changes and K changes also, correct, okay, even though the number of moles and the entropy may not change in the process. So, this deformation part is extremely important when we later do, for example, a little bit on sprays, okay, that how spray atomization and breakup and things like that also happens. Those are multiphase processes as well, as you have correctly guessed by now. So, this dE, I am just dropping the I for the time being, so that for the ease of writing. So, this is TdS, of course, this you know it is temperature, plus mu dN, this you know is the chemical potential, plus dEA SNK dA plus dEK SNA dK. Okay. Now, if the variation in the curvature is negligible, right, variation in curvature is negligible means when the droplet remains as a droplet, right. So, there is no change in curvature per se, correct. So, situations like that, for example, when a bubble actually forms, that curvature may actually remain the same. So, if this is negligible, K variation is negligible, we are just doing a special case is negligible, it can be negligible. Okay. What will happen to this particular equation? This will actually go to 0, correct. Okay. So, we can define this particular term dEA SNK, right, this term that we have over here, this can be defined as a quantity called sigma. Okay. So, that dE now becomes TdS plus mu dN plus sigma dA, right. So, this sigma is nothing but the surface tension. Got it. So, surface tension is the rate of change of internal energy with respect to area, okay, or change of internal energy with respect to area when the curvature, the number of moles and the entropy are constant. Okay. So, that is what we call the surface tension over here. Okay. So, surface tension can be also represented, okay, in terms of the Helmholtz free energy equation. See, there can be equivalent representations, right. So, Fi for example is Ei minus Tsi, right, that we know, that is the Helmholtz basic equation, right. So, similarly dFi can be written as dEi, okay, minus T dSi minus Si dt, right. So, dFi can be written as minus S Si dt plus mu dN plus sigma dA, where sigma this time will be represented as the change of Helmholtz free energy with respect to its area for constant temperature Nn. Okay. Curvature also comes into the picture, I am just dropping it for the time being because curvature we have assumed that the curvature is actually small. Got it. So, this particular thing proves that this is an alternative definition of surface tension. This is one definition that we saw over here, this is the other definition that we have over here. Okay. So, we end lecture 1 with the surface tension, that what is surface tension over here. We in the next lecture what we will do is that consider the other alternative definitions of surface tension.